In this video, we'll be looking at circuits with both resistors and capacitors, which are often called RC circuits. We'll begin by taking a charged capacitor that is in series with a resistor. We'll have a switch in our circuit so that the charge will not be able to flow until we close the switch. While the switch is open, the capacitor has some initial amount of charge on its plates, creating a potential difference equal to the charge divided by its capacitance. There is no charge moving through the circuit or no electric current, so there is no voltage dropped across the resistor. Now we'll close our switch and see what happens. We know that there will be an electric field that forms inside the wire, causing positive charges to move or current to flow from the positive plate of the capacitor to the negative plate of the capacitor. We know electrons are actually moving, but we'll describe everything in terms of positive charge in the direction of our defined electric current. As the positive charge moves off of the positive plate and neutralizes the negative charge on the other plate, this decrease in charge causes the potential difference across the capacitor plates to decrease. At any point in time, this voltage is given by the charge on the plates at that moment divided by the capacitance. Since we now have a current, there is a voltage drop across the resistor. This voltage is given by Ohm's law, or minus the current times the resistance of the resistor. Now this current will not be constant because charges will move faster when the difference in potential is greater across the capacitor. As this voltage decreases, the current will decrease and eventually go to zero when there is no potential difference across the plates and everything is electrically neutral. We can use Kirchhoff's voltage law or loop law to analyze this circuit since it is true of any circuit. If we pick any point, say the bottom left corner, and move clockwise around the loop of our circuit, the potential difference across the capacitor plus the potential difference across the resistor should sum to zero. This means we should arrive at the same potential value when we get back around. We can write the voltage across the capacitor as the charge on the plates at some time divided by the capacitance, and we can write the voltage across the resistor as the current times the resistance. These are instantaneous charge and current values at any given point while the capacitor is discharging. Now we'll do a little calculus to derive equations for the behavior of the circuit. We can write the current as the rate at which some small amount of charge dq is moving with time dt. Now the charge moving through the circuit and through the resistor is the charge coming off of the capacitor. We're calling the charge on the capacitor capital Q, and since the charge on the plates is decreasing, the small amount of charge dq in our current is minus the charge coming off of the capacitor since it is decreasing. So the minus sign here just means the charge on the plates is decreasing. And now we can plug into our equation. Now we'll divide by the resistance, and we'll move things around to isolate our dq and our dt. We'll get our capital Q's together and move our constants to the other side. Now we can integrate over the charge on the left from some initial amount of charge on the capacitor we'll call Q naught to some final charge Q. Then we'll integrate from time equals 0 to some final time t on the right. I've made our integration variable Q prime and T prime since they should be different from our limits. This is just a relabeling that doesn't affect our result since they are dummy variables which will go away when we evaluate our limits anyway. This gives us the natural log on the left that will evaluate from Q naught to Q, and we just get minus T over RC after evaluating on the right. We'll get a difference of natural logs when evaluating, which we can rewrite using the properties of logarithms. This gives the natural log of Q over Q naught is equal to minus T over RC. Now we can exponentiate both sides, which makes our natural log go away on the left. And now we can just solve for the charge Q. This is our equation for the charge on the plates of our capacitor as a function of time as the capacitor is discharging. Q naught is the initial charge, and the values of R and C are constant since they are decided when we create the circuit and put in our resistor and capacitor. Then we can find the amount of charge at some time by plugging in some time in seconds. We give a special name to this product of resistance and capacitance. This is called the time constant of our circuit. It is a property of the circuit, and we can see that it must have units of time since the argument of our exponential function should be unitless. Now we get the final form of our equation for charge. This tells us the charge on the capacitor will decrease exponentially from some initial value Q naught. We will see what this looks like in a moment. We can also get an equation for the voltage across the capacitor. Since the voltage across the capacitor at any time is given by the charge on the plates at that time divided by the capacitance, we can just divide both sides by C. This gives the voltage across the plates as a function of time, where delta V naught is the initial voltage across the fully charged capacitor. We should expect the voltage to behave like the charge since they are both proportional to each other. Now let's plot this exponential decay using our function for the voltage or potential difference. The voltage starts at some initial value, and at t equals 0, we close the switch and the capacitor begins to discharge over time. Notice that when our time t is equal to the time constant of the circuit, tau, we get e to the minus 1, which is just a number. This number comes out to be 0.37 and represents when the voltage has discharged to 37% of its original value. When two time constants have passed, the voltage is at 13%. And continuing on, after 5 or more time constants, the voltage is less than 1% and the capacitor is nearly completely discharged. Since we're only describing the behavior in terms of some number of time constants, this describes all RC circuits, and this is why we define this time constant. If we want to get the specific values, then we can calculate the actual time constant using the resistance and capacitance, and then find the voltage or charge at some desired time. The final thing we can look at is the current through the RC circuit. We can either take our equation for the charge and take the time derivative, which is our definition of current, or we can take this equation for voltage and divide by the resistance of the resistor. This works because the voltage across the capacitor and resistor must be equal in magnitude at all times, because they are the only two components in the circuit. Any potential difference across the capacitor must be dropped across the resistor by Kirchhoff's voltage rule. Doing this, we get the equation for the current, which is also an exponential decay. The only difference here is the current is 0 until the switch is closed. Then the current jumps up to some max initial value equal to the initial voltage of the capacitor divided by the resistance of the resistor. The current then falls off in the same way as the charge and voltage across the capacitor. This should also make sense since the voltages across the capacitor and resistor are equal in magnitude and the current is proportional to the voltage. Now let's look at a charging capacitor. We need a battery or a voltage source to create a potential difference across the capacitor. The battery can increase the voltage across the capacitor until it is equal to the EMF of the battery, assuming the battery is ideal. Then the battery will maintain this voltage. This is why we obviously needed to remove any voltage source to discharge the capacitor before. We'll close our switch and the battery will be able to increase the potential energy of charges from one plate of the capacitor and will move them to the other plate. This will create a current as charges move, and as the charges move onto the plates of the capacitor and build up, the voltage across the capacitor gradually increases with the charge. We'll analyze this circuit in the same way as before, using Kirchhoff's voltage or loop law. Here we know the potential difference across the battery, the resistor, and the capacitor must sum to 0. I'll move clockwise, beginning just before the battery. The voltage across the battery is the EMF of the battery. The voltage across the resistor is given by Ohm's law, or the current times the resistance, and is negative since charges lose potential energy as they move across the resistor. The voltage across the capacitor we'll just call V with a subscript C. Since the positive charges are building up on the plate that is on the same side as the positive terminal of the battery, moving from this plate to the other plate will be a drop in potential. We can write the current as dq over dt since the charge moved by the battery from the positive plate is the same charge moving through the resistor and onto the positive plate of the capacitor. This charge can be written as the capacitance times the voltage across the capacitor at that time, which again we'll call V sub C. Since the capacitance is a constant, we pull it in from the derivative after substituting. Now plugging into our loop equation, we get this. We can move the EMF and voltage across the capacitor to one side and the constants R and C on the other side with time. Then we can integrate over the voltage of the capacitor on the left and integrate over time on the right. This is a simple integral we can get using a U substitution with U equal to epsilon minus Vc. Taking a derivative with respect to V sub C, we get du is equal to minus dV sub C. This will give us another integral that results in a natural log on the left, and the right side is the same as what we got earlier. We'll also move the minus sign to the other side to make things simpler. The voltage across the capacitor starts from 0, so we'll integrate from 0 to some voltage we'll call capital V sub C. We'll again evaluate our limits and plug into the natural log, and then rewrite this difference using the properties of logarithms. Exponentiating both sides, we get rid of the natural log on the left. And now solving for the voltage across the capacitor by moving the EMF to the right and factoring, we get this final equation for the voltage across the capacitor as a function of time. Again, we see our time constant appears in the behavior of this function as well. We can plot this voltage as a function of time. If we plug in 0 for time, we get e raised to the 0th power, which is 1. This leaves 1 minus 1 in parentheses, so the voltage is 0 when time is 0 and we close our switch. After many time constants, the voltage increases until it reaches the EMF of the battery. If we let t increase toward infinity, because the argument of our exponent is negative, e raised to a very large negative exponent will tend toward 0. Then we get 1 minus 0 in parentheses, which gives the EMF times 1, so the voltage approaches the EMF of the battery. Like before, the voltage across the capacitor is proportional to the charge, so we can simply multiply by the capacitance on both sides to get an equation for the charge that has the exact same form. The current is more interesting. We'll take the equation we get for charge and take a time derivative. One term will be constant and will go away after taking a derivative. This will leave us with this equation for the current. Notice the current looks exactly as it did before when the capacitor was discharging. This happens for the same reason. The potential difference is the greatest as soon as the switch is closed, so the charges move the fastest. As charge builds up on the capacitor, the voltage across the capacitor is closer and closer to the voltage of the battery, so the current slows. We can also imagine it is more difficult to place charge on the capacitor as the plates fill with more and more charge. Finally, the charge stops when the voltages are equal. Now let's summarize and look at the complete behavior of both a discharging and charging capacitor. We'll look at the circuit at t equals 0 when the switch is closed and after a long time has passed. For a discharging capacitor, the moment the switch is closed, the capacitor is still fully charged, and the charge is at its maximum value. This means the voltage across the capacitor is also maximum, and equal to the charge on the plates divided by the capacitance. The potential difference the charges can move through is at its greatest, so the current is maximum. This current will equal the voltage across the resistor divided by the resistance using Ohm's law, and this voltage will be equal to the voltage across the capacitor. This also means the voltage across the resistor is at its maximum value. After a long time has passed, all of the charge has moved off of the capacitor, which means there is no voltage across the capacitor. With no potential difference, charges will not move. So there will be no current, and with no current moving through the resistor, there will be no voltage drop. Now for a charging capacitor. The moment we close the switch, the capacitor is still uncharged, so there is no voltage across the capacitor. The potential difference due to the battery is at its greatest, so the current is maximum. Since there is no voltage across the capacitor, the entire voltage of the battery must be dropped across the resistor. So we can find the current by taking the EMF, or the battery voltage, divided by the resistance. And we could rearrange this and write the voltage across the resistor as the current times the resistance. And again, this is just equal to the EMF. After a long time, the capacitor is fully charged, so the charge is equal to the capacitance times the EMF, which is equal to the voltage across the capacitor. Since the capacitor is fully charged, the voltage across the capacitor and battery are equal, so there will be no current, and thus there is no voltage across the resistor. There can also be no voltage across the resistor since the entire EMF of the battery is now dropped across the capacitor. That's it for RC circuits. We'll come back to these after we've looked at magnetism and add another component to our RC circuits to get RLC circuits. So that's it for this video, and I'll see you in the next one.